We're now beginning the real content of this course, which is an introduction into some of the ways that formalization and formal methods can help us to characterize properties or behavior of systems that otherwise quickly become too complex for us to understand. In this module, which I've called Systems and Proof, I'll sketch out some general principles that will apply throughout the remainder of the course. And the plan for doing that is to start by looking at some definitions of simple recursive objects, which we'll define using something called a post system. Most of this video will be about explaining what a post system is. And then we'll move on to looking at some proof techniques that are particularly well suited to working with recursively defined objects. I assume you've seen some flavor of inductive proof before now, probably what we're going to refer to as weak induction, and we'll extend that to strong induction and mutual induction. Okay, so that is the big plan, and now for the remainder of this module, we'll look at post systems, say a little bit about what they are, and use them to write some recursive definitions. Now, we have a very specific use in mind for post systems, but you want to think of them generally as a model of computation. There are a number of different models of computation out there that have been developed independently and are equivalent. One of them is Turing machines, developed by Alan Turing. Another one is the lambda calculus, developed by Alonzo Church. And then post systems, which we're introducing now, are also a model of computation. They were developed by Emil Post. And then there are other models of computation out there. So we'll talk a little bit later about what it means for something to be a model of computation. But for right now, the reason post systems are of interest to us is that we can use them to define things that are otherwise a little bit difficult to write, right? So we can define data structures or programs. And one of their handy attributes is that it's fairly easy to write recursive definitions. And what that means is that when I define some object A or some concept A, I can define it in terms of something, that I've left out here, but somewhere in this definition, I can include a reference to A or some former version of A, right? So things can be kind of defined in terms of themselves. I can also write definitions that are mutually recursive. And in this case, what's happening is I don't necessarily explicitly define A in terms of itself. I define it in terms of something else, B, but when I go to write the definition for B, I define that back in terms of A. So again, there's a mutual self-reference that's occurring here. And this allows us to write very flexible definitions of interesting objects that we want to perform proofs over. That brings us to a final key property, which is that post systems admit formal proofs. They're very precise, and so we can reason about them formally and check to see whether the definitions we've created are in fact correct. Which is to say that it actually has exactly the properties that we intended for it to have when we wrote the definition. That gives some context and motivation for our discussion of post systems. So now let's move on to say what they actually are. A post system comprises a finite set of three things. The first is variables. These are like X and Y, the things that you're used to calling variables. Signs, which are sort of like literals or constants. We'll see some examples soon. And productions or inference rules. And that latter one requires a little bit of explanation. So an inference rule looks like this. It has some number of terms on the top and a term on the bottom. And so we label the terms on the top T1 through T2, and then the one on the bottom we've just called T. And what these are is we say, well, T1 through Tn, all of these various characters for n greater than or equal to 0, they are all terms, which means they are strings of signs and variables. So those are the two things we said were in a post system in addition to productions. And we call T1 through Tn the antecedents. So this group up here, this collection of terms, those are our antecedents. And we call T the consequent. And so this is the intuitive interpretation of what an inference is. We start with some number of antecedents in our argument, some number of basic ideas that we're inferring things from, and then we end up with a conclusion, and that's what T represents on the bottom, right? Now, in the special case where n is equal to 0, then the inference rule is called an axiom, and that is a little bit tricky. But when n is equal to 0, then this list T1 through Tn is actually empty, and so in that case, this whole thing, that means there's nothing up there, right? And we just have instead just T, right? So this is a conclusion with no antecedent, and that is the meaning of axiom that you would be used to if you've seen that word. This is some statement that we have not arrived at through an inference, but we have just simply stated as the beginning of our system. And so that's the whole definition, and it's pretty simple, but I did just tell you that the POST system is a complete model for computation. So let's see some examples to explain kind of how we get to all kinds of interesting definitions and complexity just from that simple beginning. So we'll start with this POST system that just has two production rules. The first one is an axiom, and you notice there are no antecedents here. So we just, as the statement that 3 is in the set S, right? So we're going to imagine we have some set S out here, and we've been told something about it. There's a 3 in it. That's all we know so far. And the second production rule is if x is in S and y is in S, then we can conclude, this is our antecedent, we can conclude that x plus y is also in S. And it's fine in this case, just we're going to interpret everything the way that we normally have. We haven't defined addition here, but we'll assume the normal rules for addition, inclusion, and for the number 3. So even though that sounds very reasonable, I think you'll see as we move through the course that there are reasons that we may not always want to do that. And in some cases, we may want to forego our normal interpretations and instead just treat everything purely as syntactical objects. And just say, we don't know what 3 is, we don't know what plus means. We're just going to treat these purely as strings, right? And there's a number of justifications for that approach, but this is a sort of a purely formal approach. But hopefully you can see at least the analogy that when we are working with systems like machines or computers, where there is no intuition, that this is helpful still to be able to proceed without it or to reconstruct it from syntax. And in some ways, that is the project. Now, if you remember on the previous slide, we made a distinction between variables and signs. And so just point these out. The set of our signs or our literals is 3, epsilon, and plus, and our variables are x and y. And you'll see they behave a little bit differently. The literals remain fixed, but the variables do not. The variables assume the values of everything that is in the set. Whatever we have in our set S, so for example, we know we started out with 3, gets plugged in to these different variables. So in this case, if we only knew 3 was the only element we knew about in our set, we would then use it for both x and y, and we add x plus y together, then we get 6, and I'm assuming I understand that, so I'm putting 6 then back into the set, and this way I sort of continue to expand what I understand to be in the set based on following this recursion rule. Now I can do it again, and the second time through I might choose 3 and 6, so then I would have 3 plus 6 is also in the set. And by repeating this rule, I discover more and more of its elements. Now you'll see on the next slide how we can use the POST system notation to prove that a particular element is in the set, but we also might want to characterize what exactly we've defined. So one way to start is to make a claim about what it is that we think we define. So I could say, I think that this system defines the set of all positive multiples of 3. Now, that sounds pretty reasonable, but in order for me to feel very confident that that is actually true, I need to write a proof. And the statement I'd want to prove is that n is in S if and only if n is a positive multiple of 3. It's just a slight restatement of the claim above. Now this is an if and only if statement, so I need to prove it in two directions. The first one is n is in S only if n is a positive multiple of 3, and that represents system soundness, right? Meaning that there are no undesirable things that have somehow gotten into my system. There's no things in it that are not positive multiples of 3. This doesn't mean I have all the desirable things in it. I don't necessarily know that I have all of my positive multiples of 3. That is the next statement that I have to prove, right? And that is n is in F if n is a positive multiple 3. That's a completeness result. That means I do, in fact, have all positive multiples of 3 in my set. It's worth pointing out before we move on that you really need both soundness and completeness before you can say that you've done a good job in defining your set, right? Having one but not the other is not kind of like being halfway there. And that's because it's typically very easy to define systems that are sound but not complete, or complete but not sound. And the way you would do that is if I just don't have anything in my set at all, if my set is an empty set, well then I know that there's no numbers in it that aren't positive multiples of 3. So the empty set is sound, right? And if I, on the other hand, take everything in my set and I just put all numbers in it, and have it be the entire set of natural numbers, well, it's certainly going to be complete. But again, this doesn't really make much progress towards solving my problem. At any rate, we will come back to a discussion of how you're going to prove those two statements when we talk about induction and how you can write an inductive proof for a post system. But first, what we can do is show a relatively easy proof showing that a particular element, in this case 9, is in a set defined by a post system. So we have to use the rules repeatedly until we derive 9. And this kind of derivation is a legitimate form of proving that an element is in a set. We start with the axiom, right? We say, okay, we know we can always make this claim 3 is in S because that was given to us as an axiom. And we can use it as many times as we like, right? We are allowed to draw on it multiple times. And what we're going to do is create one for each of the inputs in our inference rule, R, right? And now I'm using R here. Remember, this is our X and this is our Y. And I use that to generate a 3 plus 3 and say, okay, that's in my set. So now I've used the axioms and one application of R. And this notation I'm writing out is just using the same notation for inference from the post system. So then I pull in another axiom. In this case, I need another 3, right? I know I'm headed for 9. And I know I can now repeat this inference rule, this R, right? My first rule. And so I repeat it, and now I have 3 plus 3 plus 3 is in S, right? And I use my intuitive knowledge of what 3 plus 3 plus 3 is to conclude that that is 9, and I have now completed a derivation of 9 in this post system. This form of writing a derivation might take a little getting used to, but remember how we defined our post system, right? We had a base case and this rule, and what we're doing is simply making inferences using these two production rules, right? That is what they're for. So the base case, we can make this claim whenever, and we're trying to sort of set up X's and Y's that will allow us to use this rule, or R, to get to further elements in the system. And so that's all that's happening here. I have these two base cases that I set up first, right? And then I here am applying rule R, where I'm using, this is my X and this is my Y, and that's what the first application gets me to this second level here. Now what happens is my 3 plus 3, this whole thing becomes a new X. And over here I use my base case to generate another Y. And then again, I'm simply applying my rule R, which allows me to draw the horizontal line for my inference and get down to the element that I'm looking for. That's just a recap in case that helps make it clear what we're doing here. You will probably want to practice a few of these. So hopefully that gives you some idea of what a post system looks like and sort of generally what post systems are about. In the next video, we'll look at some more examples of definitions using post systems and some variations of how we might write these definitions and the types of systems we can define with them.